Hi everybody, my name is Dr. Josh Redstone, and I'm a cognitive scientist and philosopher currently teaching out of the philosophy department at Carleton University in Ottawa, Ontario. I've been tasked with putting together a little teaching demonstration for you all today. So what I thought I would do is design a brief lecture around a question that I often hear from some of my students. As you can imagine, one question that I often get is, can machines actually think? This is something I explore quite a lot, especially in some of my first year philosophy seminars. I personally think this question is better formulated as, is what machines do, machines like computers, best characterized as thinking or as something cognitive? So that's sort of what I mean when I ask the question, can machines think, in this lecture. Now, I don't think that I'll be able to provide you with a satisfactory answer to this question today, but what I hope to be able to do is equip you with some tools, both philosophical and scientific, for thinking about this question. So if you get to the end of this lecture and you're still not certain about whether machines can think, or you find yourself even less certain about whether machines can think, that's okay, because hopefully you will be better equipped to think about the question, can machines think? All right, let's get rocking. I'd like to explore this question with you by taking a look at some of the work of Alan Matheson Turing, a computer scientist, indeed one of the originators of computer science and artificial intelligence, mathematician, and yes, philosopher. Let's start with a little bit about Alan Turing himself on slide number 2. Alan Turing was born in London, United Kingdom in 1912. He got a bachelor's degree in mathematics from Cambridge University, and he would complete his PhD studies at Princeton University in the United States under the supervision of Alonzo Church. While Turing was at Cambridge, he published a very influential paper where he introduces the notion of something that's come to be known as a Turing machine. Keep this in mind because this is going to become important later. Of course, Turing famously worked as a cryptographer at Bletchley Park during the Second World War, where he helped lead efforts to decrypt and decipher secret Nazi messages that were sent using the Enigma machine. Specifically, he helped lead the design of a digital computer called the Bomb, which could work out the settings on these Enigma machines that the Nazis were using so that the Allies could more easily decrypt their secret messages. In 1952, during an investigation into the burgling of his house by one Arnold Murray, it was discovered that Alan Turing had been in a romantic relationship with Murray. And of course, homosexual behavior, homosexuality itself, was still criminalized in the United Kingdom at this time. Turing was charged and convicted with gross indecency, the same charge brought against Oscar Wilde, in fact, previously. He was faced with the choice of either prison time or chemical castration via a sort of hormone therapy, and he chose the latter, and this resulted in substantial changes to his body as well as his mood. In 1954, Turing was found dead in his home at the age of 41, just shy of his 42nd birthday, of cyanide poisoning. Now, there's some contention over whether the poisoning was accidental or whether Turing died by suicide, but either way, we can all agree that it was a tragic end to a short but brilliant life. So why are we looking at Alan Turing? Well, besides being an originator of artificial intelligence and computer science, Turing not only formalized the concept of computation, but also introduced something called the imitation game. Nowadays, we tend to call the imitation game the Turing test, a test that is supposed to reveal whether machines can think. The kinds of machines that we're talking about today are, of course, digital computers. Now, Turing did not invent the digital computer. That honor actually goes to Charles Babbage, who was a Lucasian professor at Cambridge University, the Lucasian professor of mathematics, that is. Babbage designed what was essentially a digital computer, but never completed construction of it. But it was Turing who later would formalize the notion of computation using the notion of an algorithm, which is a sort of set of rules for transforming inputs to outputs in a definite and circumscribed manner. The sorts of digital computers that Turing talks about in his 1936 paper on computable numbers are Turing machines, or what have come to be known as Turing machines. They're an imaginary type of digital computer. Now, Turing introduces this notion because he's trying to provide an answer or a solution, rather, to something known as the halting problem. Now, what is the halting problem? Well, imagine that you've got a computer program that's designed to, do a particular task. You want to know if your computer program will deliver you a solution to the problem, or whether it will just continue on forever and ever, never giving you a result. What a solution to the halting problem would give you is essentially a means of knowing whether your computer program would deliver a solution or whether it would just kind of keep on looping forever. Now, it's important to emphasize that these machines are imaginary or conceptual. Turing never built one, but they nonetheless have certain important parts that you need to know about. Turing machines, of course, have a machine table, which contains instructions for the machine, what we might call a computer program today. It's got a machine head, which can read and write symbols. These symbols represent information. The symbols can be typed or removed from a tape with cells. So you can have one symbol in each cell on the tape, which represents information. The tape, of course, can be moved back and forward, and we can implement different kinds of programs on different kinds of specialized Turing machines. How did Turing accomplish this if Turing machines are imaginary or conceptual? Well, everything about Turing machines, the states that they're in, their program, their inputs, their outputs, we can represent all of this as sequences of numbers, and that allowed Turing to derive mathematical proofs about the properties of Turing machines. That was how he was able to demonstrate that there is no solution to the halting problem and that there exists a special kind of Turing machine called a universal Turing machine. These universal Turing machines are the theoretical forerunners of modern digital computers, like the one I'm using right now to record this lecture, or the other one that I'm using right now with my lecture notes displayed on its screen. A moment ago I said that Turing formalized the notion of computation. So what is computation? Well, computation is the rule-governed transformation of representations. Representations of what? Of information. So computation is a very mechanical process. You have some inputs, you have some kind of rule-governed transformation of those inputs, and then you have outputs. Now, thanks to Turing, as well as other thinkers like Alonzo Church, Alan Newell, Herbert Simon, Hilary Putnam, and many others, a theory of mind would eventually emerge in the 20th century called the computational representational theory of mind. This theory essentially says that the human mind is a computer. Now, this is going to be important for later when we circle back around to the Turing test and what it's actually good for. Cognitive scientist Jose Luis Bermudez says that computation is what computers do, and according to many cognitive scientists, it is what minds do. It's thanks to Turing that not only do we have a formal notion of computation, but it's also thanks to Turing in an important sense that we have the computational representational theory of mind as well. And as I said, this will be important for later. But for now, you have some idea of what digital computers are. To quickly recap, digital computers are discrete state machines that transform inputs to outputs using rules, algorithms. Computers take in information, which is, represented in some way. Those representations are transformed according to an algorithm, a step-by-step sort of rule-governed process. And then we have some sort of outputs that the computer will delivered to us. This is simple, but it is fundamentally how computers work. Now let's return to the question at hand, can machines think? Which I'm going to call the big question, following Stuart Schieber. Now, Turing, in his 1950 paper, Computing Machinery and Intelligence, says right off the bat that he thinks that this question is, quote, too meaningless to deserve discussion, end quote. Why is it too meaningless to deserve discussion? Well, just ask yourself, what is thinking? What is a machine? Many people disagree on the answers to these questions. Some people think that the human being is a machine. Some philosophers, I should say. Some people do not. Some people think that thinking is a mechanical process, like Turing. Some people think that thinking is a function of the soul, right? So we could spend time on these questions until the cows come home, and we'll never be able to answer the big question, says Turing. Of course, it's kind of funny because Turing does spend quite a lot of time in this paper discussing the particular kind of machine in question, digital computers, right? But let's set that aside for now. So Turing does not try to tackle the big question head on. Instead, he sort of operationalizes it. Now, what is operationalism? Operationalism is an idea you see quite often in psychology, and basically it's the idea that you want to measure something, but maybe the thing that you want to measure is something that you can't directly observe. So what you do instead is you measure something that you can directly observe that everyone agrees is related to the unobservable thing that you're actually interested in. In this case, Turing is interested in measuring or determining whether a machine can think. Now, we can't directly measure thinking or intelligence, right? But one thing that we can observe and measure, which everybody agrees is associated with intelligence and thinking, is verbal behavior or language. Turing operationalizes this question by proposing the imitation game, which is, as Stuart Schieber describes it, a game-theoretic crystallization of Descartes' observation that flexibility of verbal behavior is the hallmark of humanness. We'll come back and revisit this idea shortly. So, how does the imitation game work? Well, the original formulation of the imitation game features 3 players. We have player A, who is a man, player B, who is a woman, and player C, who could be of any gender. C is our interrogator, and their job is to ask A and B questions toward the end of identifying which is the man and which is the woman. Is A the man or the woman, or is B the man and the woman, or the woman? That is C's job in this game. Of course, C cannot hear A or B, nor can they see A or B. Wow, that was a mouthful. So, we've got A who's trying to fool C, B who is trying to assist C in coming to the right answer, and C who's interrogating A and B, asking them questions, trying to determine who is the man and who is the woman. Turing then asks, what will happen when a machine takes the place of A in this game? So now A is no longer a human player, A is a machine trying to convince C that it is in fact a man. If that all sounds more complicated than how you usually think of the Turing test, well, that's probably because in his later writings, Turing would actually simplify this scenario quite a bit. In later writings, Turing imagines 2 players. One player is either a human or a machine. We'll call that player 1. The other is the interrogator, and the interrogator is always human. As in the first game, the interrogator is asking player 1 questions with the aim of identifying whether player 1 is a human or a digital computer. The interrogator does this by asking questions in a viva voce style examination. Viva voce, by the way, is Latin for in living voice. A viva voce examination is a bit like what I'm doing right now. It is an examination designed to reveal whether you actually understand what you're talking about or whether you have simply learned everything by rote. It's the kind of thing you do if you, when you defend your master's thesis or your PhD thesis. So the interrogator engages with player one in a human-like conversation. And if at the end of the test, the interrogator cannot tell whether player one is a human or a machine, then the test is passed. Revisiting operationalism, how do we know, why is the test passed if the human player can't tell whether she's interacting with a machine or a human? Well, whether it's a machine or a human, it is doing something that we all agree intelligent things can do. And that is holding a conversation, holding a human-like conversation. So according to Turing, if a machine can do that, we have to say that whatever that machine is doing, it's thinking. Earlier I mentioned that Schieber thinks of Turing tests as a sort of game theoretic crystallization of Descartes' observations about human verbal behavior as the hallmark of thought, of the rational soul. And if you have a background in philosophy, you've probably also noticed this yourself if you've ever read Turing's work on the imitation game. There is certainly a very Cartesian flavor about the Turing test. Others have pointed this out as well. René Descartes wrote in the Discourse on the Method, published in 1637, that, quote, "If there were machines bearing the image of our bodies and capable of imitating our actions as far as it is morally possible, there would still remain two most certain tests whereby to know that they were not therefore really men. Of these, the first is that they could never use words or other signs arranged in such a manner as is competent to us in order to declare our thoughts to others. The second test is that although such machines might execute many things with equal or perhaps greater perfection than any of us, they would without doubt fail in certain others, from which it could be discovered that they did not act from knowledge, but solely from the disposition of their organs." So Descartes is saying that, well, there are two things that machines cannot do. They can't use words to declare their thoughts to others, and they act mechanically, deterministically, and not originally like human beings do. They cannot use reason as a universal instrument the way that human beings can. So Turing thinks the big question, can machines think, is too meaningless to deserve discussion. Nonetheless, he spends a good deal of time in his paper on computing machinery and intelligence defining exactly what kind of machine he thinks might be able to think. And that machine is, of course, the digital computer. I want to show you some examples now of using the Turing test as an actual empirical test. And one of the textbook examples of this is ELIZA. ELIZA was one of the first chatbots programmed to behave like a Rogerian psychotherapist or a humanist psychotherapist, named after the humanist psychology tradition of Carl Rogers. ELIZA was a very simple program. It was created by Joseph Weizenbaum in the 1960s at MIT. It used only about 200 lines of code, a lot of canned responses, a lot of rearranging of what was fed to it to produce an output. Of course, ELIZA is not very impressive by today's standards, but are there machines that we could test which may pass the Turing test that might be a little bit more impressive than ELIZA? Or ELIZA? ELIZA? Yes, the answer is yes. You have probably heard of ChatGPT. ChatGPT-4 is the latest iteration of ChatGPT, which is a natural language artificial intelligence. Now, ChatGPT is pretty cool. ChatGPT has been trained on loads and loads of text, from the internet, lots and lots of natural language text. And what it does is it takes in a prompt from a human user and then generates a response by guessing, based upon all of the billions and billions of sentences that it's read, what word is most likely to come next in the sentence. And it thusly generates a reply. I wanted to see what ChatGPT-4 was capable of, so I asked it to explain the Turing test to me, and I got to admit, I was pretty impressed with the answer it gave. So does ChatGPT pass the Turing test? Not really, no. It is very impressive, but it also sometimes fails to convincingly behave intelligently. Here's an example. I asked ChatGPT-4 to review and critique Alan Turing's instructional chess book entitled Chess for Machines. Here is the answer, or partial answer, which ChatGPT gave me. First, ChatGPT gave me a disclaimer. It said, as an AI language model, I am not capable of reviewing any book or providing critiques. However, I can give a brief overview of Alan Turing's instructional chess book entitled Chess for Machines. So let's bracket the fact that ChatGPT just told me it's a machine. Let's forget that and just evaluate what it says about Alan Turing's book here. Alan Turing's Chess for Machines is considered a groundbreaking work in the field of artificial intelligence and computer science. Published posthumously in 1952, the book aimed to teach computers how to play chess, a complex strategy game that requires skills such as pattern recognition, decision-making, and strategic thinking. So how do I know that ChatGPT doesn't pass the Turing test based on its verbal behavior? Well, Alan Turing never wrote a book called Chess for Machines. I just made that up. What I did just now was make ChatGPT hallucinate. So ChatGPT will sometimes have these hallucinations where it just makes stuff up. And that's because ChatGPT doesn't really know anything. Well, so much for the Turing test as an empirical test. What about as a thought experiment? So imagine that if you were having a human-like conversation with a computer and you decided that after 5 or 10 minutes of interacting with it, you could not tell whether you were talking to a machine or a human. Would you say that that means that whatever you were talking to was a thinking agent? You might answer yes to this question, right? You might say yes. If I could hold an intelligent conversation with, a machine, I would have to say that the machine is thinking. Whatever it's doing, it's behaving intelligently, it's thinking. You might disagree, though. You might say that no, the machine is not thinking. It is pretending, or it's fooling me, perhaps, into thinking that the machine can think. You might say that yes, it is conceivable that a suitably programmed computer could behave intelligently. Its verbal behavior is on a par with a human. It's conceivable that we could make such a machine, and if we did, we would have to grant that that machine has intelligence. You might offer that answer if you think that thinking is a mechanical, step-by-step sort of computational process, right? If you think that thinking is computation, if you think cognition is computation, then yeah, why not? There's no barrier there's no reason not to say that the machine is intelligent if it can do something that we all agree intelligent agents can do, namely hold a conversation. So if you're a computationalist, like if you subscribe to the computational representational theory of mind, or perhaps if you're a functionalist as well, you would probably say, yes, this is conceivable, to use the Turing test, to think of the Turing test in this way. If you believe that thinking is a function of the soul, or if you believe that thinking is a function of brains and only brains and not mechanical systems like digital computers, then you'll probably answer no to this question. Well, time is short, so I suppose we better wrap this brief lecture up. So can we answer the big question today? Well, certainly not. There's definitely not enough time, and I've spent years thinking about this question. And to be honest with you, I'm still not sure myself how to answer the question, can machines think? One thing I can tell you, though, is that now you should have some more tools in your philosophical toolbox for thinking about questions such as, can machines think? Or whether what digital computers do is best characterized as thinking. Now you know about digital computers and the imitation game, nowadays known as the Turing test, and you know that the Turing test has multiple different uses. We can apply it in different ways. If you're using the Turing test as an empirical test to answer the question, can machines think? Well, then the answer is going to depend on how well the machine performs. Does the machine convincingly perform like a human being? Are you unable to tell whether you're conversing with a human or a machine? Is that computer using reason universally and declaring its thoughts to you using language? If it seems to be doing that, it passes the test. If you're using the Turing test as a sort of thought experiment, well, the answer to whether machines can think really depends upon your own beliefs about minds, machines, brains, artificial intelligence, and all of that stuff. I suppose if you're using the Turing test as a thought experiment, you're not really answering the big question in the same way as you are when you use the Turing test as an empirical test. Rather, what you're doing is clarifying your fundamental beliefs about what machines are actually capable of. As I argued in my PhD thesis, I think we can also use Turing tests reflexively. That is, I think we can use them not just for answering empirical questions about machines or for clarifying our fundamental concepts about machines, minds, and thinking. We can use them to answer questions about ourselves and how we interact with thinking machines. And that's what my PhD thesis was all about. And full circle moment, you might think that the Turing test is useless. After all, remember, Turing does not spend very much time at all trying to define thinking, even though I think that he did believe there was something that it meant to be a thinking agent, namely domain general reasoning, natural language, and using these two things originally. Well, everyone, that's all for today. I hope that you found my little teaching demonstration interesting and informative, and I hope that I've equipped you with some interesting tools for your philosophical toolbox when it comes to thinking about minds, machines, brains, artificial intelligence, and all of that lovely stuff. I hope you found the learning materials that I included with this lecture helpful, namely my PowerPoint slides and my little handout, and I look forward to taking your questions. So thanks, everyone. Bye for now.